Okay. Well, if no, for me it means like everybody is happy, things moving smoothly. Just be aware that, this is pretty much the sort of feedback channel I can get here is just from you, right? And so if you feel we need to change something with the course or things not going the way we would like them to go, or, something is, well, can be changed with seminars or labs, lectures, just you need to let me know, okay? All right. So let's get started. We're going to cover two more topics today. We'll start with random graphs. Let's just a little bit talk about it and see where and how it fits into the bigger picture. So we talked last time on the previous lecture about like empirical network features, right? So the real world networks and their properties. And we saw and we discussed that the real world networks, they're usually power law distributed or heavy tail distribution, degree distribution, right? Which is a lot of nodes with low degree, and there are some nodes with a very, very high degree. Then we talked about the graph diameter, so that those networks have quite small graph diameter or average distance, right? So there's sort of small world. It's very easy to get from one node into this network to any other node. And then we talked about the fact that a lot of networks, especially those that come from from social world, from like social networks, they have pretty large clustering coefficient, or the other word for this is transitivity. So the fact that if there are two nodes, if there is a node and it's connected to two nodes, those two nodes most likely connected among themselves, and so there is a lot of triangles in the graph, okay? So these are like sort of three fundamental properties we discussed last time, and most of the real-world networks possess those properties. Now, what we're going to do today is we're going to talk about network models. Now, this is an artificial model, right? We're going to try to come up with a particular model. We think that we want to describe some of those properties, literally, right? We would like to make a model that generates a network that might be similar to what we see in real life. Now, why would we want to do modeling in general? So what is it good for? I mean, not necessarily, not only here, but in general, why do people do models? In economics and physics and you name it. People do models. Why do we do models? For prediction, evaluation, optimization. So I mean, the thing is, there are certain situations where you can make experiments, right? Then you might not necessarily need models. But then there are situations like in economics or in here, if you have a network, well, you might ask a question, what if, right? You want to play scenarios, what if, but you cannot if you don't have a model. Plus, models typically is a simplified representation of reality, right? So on one hand, you want it to represent the reality, right? Because that's what you're trying to model. On the other hand, you sort of want to make it simplified, right? So you have a few knobs you can turn and you can sort of see the effect, right? If your model is as complex as a reality, well, I mean, it's not such a great model, right? Because then it's going to be very, very hard to explain what's going on. So bottom line, we want to build something that by using this model, by using those models, we want to be able to generate networks. And we want those networks that we generate look like the real world networks. Then we can make certain assumptions. We can say, okay, well, look, here is the mechanisms by which those networks, we generated those networks using our model. And, the networks look like real world. So we can make certain assumption about how those real world networks happened, right? We can say, okay, maybe this was the mechanism how they were formed. Plus, as you mentioned, we can also use this to, maybe investigate certain properties, right? Change parameters, see how things changes with the networks, or maybe, build certain optimizations, right? But in any case, we want to model, and the model is generative model, which means it generates, it creates networks. Okay? Make sense? All right. So we're going to look into three different classes of models. The first one, it's a random graph model. And in fact, this is like sort of the oldest model, goes back to 1959 proposed by Erdős-Rényi. And that's like sort of pure, beautiful mathematics behind it. Then we're going to talk about two other models, more sort of contemporary models that were created when this whole thing with network science started around 2000. And that's going to be a small world model by Watson-Strogatz and preferential attachment model by Albert Barabashi. Albert Barabashi is a guy whose textbook we're using, right? And so actually, if you look into his textbook, there are probably 2 or 3 chapters dedicated to his model and sort of different variants of that model. And that model made him, famous in network science. Okay? So let's move on. Let's think about this random graph model. So the idea is the following. Well, first of all, what do we call, random graph, right? And now let's think about maybe not a huge network, but some sort of smallish network. And we can define it in 2 different ways. Interestingly enough, mathematical properties of both approaches at large number, when you have large number of nodes, they become very similar, and so you can actually use any of those 2 models. But the idea is the following. One way to think about random graphs is the following way. Let's say what's given to you is number of nodes and number of edges, n and m, okay? Now, let's say we can, from those n and m, we can generate the universe of graphs, all the possible graphs that has n nodes and m edges. All right? So how many of those graphs can we generate? Well, if you have n nodes, how many pairs of nodes are in there? Because a graph, right? A graph, it's an edges connecting nodes. If we have n nodes, how many of pairs of nodes we can have? Oh, come on. N nodes, how many pairs can we form? Yeah, n combination of 2, or in other words, if I just try to wave my hands, it's going to be n times n minus 1 over 2, right? Why? Well, because there is n ways to pick up the first node, right? There is n minus 1 ways to pick up the second node. So total number of n times n minus 1 of pairs, but then I double count because, I can pick up this edge and then I can pick up the back edge, and so that's why I divide by 2. All right? So this is the total number of of pairs you can create there. Now, if you have m edges, physical m edges, right? And you have n times n minus 1 over 2 possibilities to place them, so the total number of different placements will be Cm over m, right? So how many combinations, how many ways to place m over this capital N. So now, that's how many graphs you can generate. There'll be different graphs, but that's how many of them you can generate. And then you can think about random graph as just like say, okay, you have this big bucket of graphs. You just go there and you pick up one randomly without looking. That's your random graph. Okay? So that graph will have exactly n nodes and m edges. And it's going to be a random graph because you pick it up just randomly out of all the graphs that's possible with this number of nodes and edges. So that's one way to do it. Another way to do this, and that's actually a much more constructive way, is to have a different parameterization, to use as a parameters number of nodes, n nodes, and then introduce a parameter p, which is a probability that 2 nodes are connected. Okay? So if that probability, so that any 2 nodes in the graph are connected. If this p is equal to 0, then there is no edges in the graph. It's just nodes. If this p is equal to 1, then every pair of nodes is connected, right? And so you have a complete graph with every node connected to every other node. So the p is parameter. Going from 0 to 1, you go from absolutely empty graph to completely full graph. And then there are a lot of things happens in between. Now, practically speaking, when you build this kind of a graph, what you do is you just go through all the pairs, one by pair by pair by pair by pair. For each pair, you literally flip a coin. And let's say if p is equal to 0.5, right, you flip a coin and you decide where they're connected or not. If P is like less than that, of course, you know, that's how your probability works. Well, then there is less chance that they're connected. And you just go through all the pairs, and that's how you build your graph. So in this case, the parameters that are given, that I used, is n, which is number of nodes, and p, which is the probability that two nodes are connected. These are two numbers that are needed to generate this graph. But the number of edges that's going to be formed in each of those graphs is a random number. Because if you run this simulation as I described once, you'll get some number of edges. You run it again, because it's a probabilistic story, right? You run it again, there'll be different number of edges generated. You run it a third time, there'll be another different number of edges generated. Make sense? Okay? So, in this approach, what you actually can calculate is an expected number of edges in this type of graph, or average number of edges. And that average number of edges will be what? Will be probability that two edges connected times the total possible number of pairs. Possible number of pairs we already computed, it's n times n minus 1 over 2. And then for each pair, there is a probability that's connected, it's p. And then expected number of edges is given by that formula. If p is 0, expected number of edges is 0, it means nothing is connected. If p is equal to 1, you know, every pair is connected, and we have a full graph. And, you know, when p is in between, well, that's the expected number of edges. Right? So the difference between two models, in the first model, you have fixed number of nodes and fixed number of edges. In the second model, you have fixed number of nodes and the parameter that tells you the probability that any two nodes are connected. And in terms of construction of the graphs, that's much more efficient. Yes, please.
When you say connected, you mean like directly connected by the edge?
By the edge, yes. Yeah. No, yeah, I'm sorry. Yes, when I say connected, meaning directly connected by the edge, right? So one node, second node, there is an edge between them. Okay? Make sense? Okay. All right. Now, if we can estimate or compute this average number of edges in the graph, then we can, for example, calculate easily expected or average node degree in the graph, right? Okay, again, if p is equal to 0, what's average node degree in the graph? 0, right? They're all disconnected. If p is equal to 1, what would be the average node degree in the graph? N minus 1, right? Because you pick up one node, so what's maximum possible is n minus 1. If n is large, it's order of n. So you can calculate average node degree k is you just add up all the node degrees, 1 over n. Now, interestingly enough, and I recommend you to try this and prove it, it's kind of very easy identity, but very helpful. The sum of all node degrees in the graph, what is it equal to? Think about it. Just draw a simple graph. Draw a triangle.
Sum of degrees multiplied by 2.
Almost, but not degrees. Number of edges. Just think about this. Take two nodes connected with an edge. Node degree 1, node degree 1, right? Sum of node degrees is 2. There is one edge. Twice the number of edges is the total sum of node degrees. Draw a triangle. The same story, right? And then if you think about it, you realize that's, yeah, of course, that's the way it should be, because, every edge contributes to degrees of two nodes, right? Because there is always, it starts somewhere and ends somewhere, right? You don't believe me, you draw a triangle, kind of, you'll understand this. Okay, so sum of the all node degrees is 2 times number of edges. Now, in this case, because we talked about a randomly generated graph, we're talking about expected number of edges, so 2 times sort of average m divided by n. Plug in the number, plug in the formula, it gets p times n minus 1. When n is large, it's p times n. So average node degree here is a probability that two nodes are connected times the total number of nodes. Now, this identity, this is extremely important formula. We're going to be using it through the entire lecture. So average node degree is p times n. Right? Make sense? Good. And you can also calculate the property which is well known in mathematics, which is the density of the graph, right? Which is the total number of edges divided by the maximum possible number of edges that exist in the graph. maximum possible number n minus 1 over 2, right? This is when graph is fully connected. M is what we get here. If you put in the numbers in there, you realize that the graph density is actually equal to this parameter P. So you can think about the model here, this parameter P that controls the model, right? That controls the probability that two nodes are connected is in fact just the graph density. And it makes sense, right? If it is 0, nothing is connected. If it's 1, it's completely full, right? And everywhere in between. So P has this meaning of density of the graph, density of the edges in the graph. All right, now let me know if I'm too slow, I'll speed it up. If I'm too fast, I'll slow it down. What is it? Doing fine? All right. Because I see some faces over there, back there, like bored, and I'm like, okay, well, fine, we can go faster. Okay, so the next step is, remember, we wanted to, build a model, and we just came up with the approach, right? We said, okay, we're going to generate random graphs in a certain way. This is our approach to generating graphs. Now we need to try to estimate certain properties. And since we talked about degree distribution, clustering coefficient, and the diameter, we want to see if for this particular model, we can actually calculate them. And in fact, for this model, we can. So first of all, let's try to calculate node degree distribution, which is what is the probability that particular node has a degree k, or has k neighbors when you have this type of a construction, right? So that's actually very easy. Remember what we do. We pick up a node, right? Remember how I described the construction of the graph. Go through all the pairs and see if they're connected with a probability P. So if you think about this, one of the ways to do it, you pick up a node, right? Then you go through all the possible connections from this node, which means to each and every node, right? And there's a probability P that it is connected. And if you're actually constructing this graph, you like sort of flipping a coin and you're connecting it or not, whether it is, depending on on what coin shows. But if you try to calculate the probability of the node degree, right? It's a probability of how many connections are going to be formed. So the total number of connections it could possibly form is n minus 1. For the node to have a degree k, it should get k edges connecting it, and also should not get n minus 1 minus k, so the leftover should not be connected, right? Out of total number of n minus 1 connections, k should exist, and the leftover, which is n minus k minus 1, should not exist. And that should happen like simultaneously, right? So that means if you think about probability, the probability that things are connected p, you need to have, it should have k connections, so it p to the power k, and should not be connected to everybody else. That means 1 minus p, n minus 1 minus k. And then out of this universe of n minus 1 nodes, how many ways to connect with k edges to them? How to select, how to select k nodes out of the neighborhood to get connected to? Well, it's ck out of n minus 1. And that's where this formula comes from. You should have seen this formula in probability theory. There is a very well-known problem, which is actually just, you can describe it exactly the same way. When you have a target, right, and you're shooting the target, and there's a probability that you actually hit the target, how many, for example, what's the probability that after you make 5 shots out of 10, that, what's the probability that when you that, for example, you hit the target 5 times out of 10 shots, right? Exactly the same problem. Make sense? All right. Okay, so that's called Bernoulli distribution. Now, what's interesting, if we can actually go and take this distribution and go to some limits when n goes to infinity. Why do we want to take n to infinity? Well, because again, if we want to do some sort of theory, you would like to make it quite universal. You would like to think about big graph. So n goes to infinity, graph growing. So you kind of avoid boundary effects. Everything is nice. The only problem is if you just make n grow, right, the whole thing will blow up. So you need to have control over certain parameters. And so one of the ways this you can consider this limit is you can increase n, but at the same time you, for example, can decrease probability of the connections of the nodes. And so what you do is you take p times n, which is in our case is average node degree. Keep it fixed, grow the graph, but then p is decreasing. All right? Now this is just a trick. You go from Bernoulli distribution to continuous distribution, which is a Poisson, right? And then you see the classical Poisson formula. Sometimes in this theory you use average case, sometimes you use lambda, as a symbol. It's all the same. So now what this formula says, it says the probability of a node to have certain degree, right? To have a degree k. So probability of a node to have a degree 1 is equal lambda to power 1 e to the minus lambda divided by 1 factorial. Probability that we have a node with degree 2 is equal lambda squared e minus lambda divided by 2 factorial. And so on and so forth, right? So probability of a node to have certain degree, it also tells you on average how many nodes of which degrees are presented in the network, right? So it's degree distribution. And if you plot it, well, that's what it's look like. I mean, again, I hope you have seen previously, Poisson, Bernoulli distribution, Poisson distribution. That's sort of the typical distribution, which has, very well-defined peak in the distribution, and then it just drops down with exponential tail. Now, we should pause here because this distribution doesn't look like power law distribution, right? And it is not. So right here we can right away say that this model, this random graph model, is actually not describing the real world networks in terms of the degree distributions. So in real world networks, we have a lot of nodes with small degrees, right? And few nodes with very large degree, and then the distribution drops that way. Here, we see that, it's bell-shaped distribution, right? It actually tells you that the majority of the node degree will be, let's say, if lambda is 10, majority of the node degrees is 10, and then there's some nodes with smaller degrees and some nodes with larger degrees. So this model generates graph with a different degree distribution than what we see in real-world networks. And this is a very interesting story because until this year 2000, before people actually measured the degree distribution, at the sort of beginning of internet age, people believed that the internet as a graph, and that's the first graph that has been studied, as a large graph, that it actually obeys this random graph law, that it is created randomly, because you think about, look, the web is sort of random, right? Because people connect and point to other people, so it should be random. But when we start measuring, the distribution was not. And so this model does not describe how the actual physical graph has been created, and that's what caused people like Barabashi to start thinking about different models. So the fact that this model, mathematicians since 1960s believe describes all the network, it didn't describe the network that was measured around 2000 in the internet. That caused people to start looking for new models. Okay? So now, then you might ask, why the hell we're talking about this if it's not the right model for what we see in the real world? Well, the reason is because it's not only because this is sort of grandfather of all the models that we have out there, it's also because it's actually a very clean mathematical model, and you can calculate a lot of things for this model that you cannot calculate for other models, and you can do it analytically. Plus, it's a kind of starting point for a lot of models. So when you understand this model, you start understanding how other models behave. So in some sense, it's like a little bit of theoretical exercise, but it is a very valuable exercise, right? It gives you very, very good, grab on random properties of the network. So we're going to talk a little bit more about this model and see some of its properties, and actually some of those properties are really, really fascinating. So actually this is a random graph, right? So that's what it looks like, right? This is I generated this graph with average node degree equal to 5. Then the distribution is that bell shape with maximum at 5, which means majority of the nodes, will have node degree 5. And then, tails to the left, to the right. That's what it looks like if you actually generate it, right? And you can just generate it either by literally using the procedures that I have described, or in network X, you just call the function, right? Generate a random graph, and it's going to generate your graph with its parameters. Now, what's really interesting with these graphs is the following situation. Think about it. When P density or the probability of connecting is equal to 0, it's empty graph. There's no connections. When it is very large, when P is equal to 1, everything is connected. So somewhere in between, something funny is happening. At the beginning, you cannot get from any node to any other node. At the end, you can get from any node to any node in one step, right? So probably somewhere in between, and that's, hypothesis. There might be a situation where all of a sudden you become capable of getting from any node to any node, maybe not in one step, but actually they just become connected, right? So, think about, I don't know, people digging channels, and then at some moment with certain density of those channels, they kind of becoming connected. And you can get from any point to any other point. So in fact, this is called phase transition, where the property of your system changes drastically. From the situation when you cannot get from any node to any other node, all of a sudden, you can't get from any node to any other node. And then when the P increases more, then this sort of distance is getting shorter and shorter and shorter, and eventually you can get in one step. But the principal difference happens in between situations when you cannot get from any node to any other node to the situation when you can get from any node to any other node, right? So graph becomes connected. In fact, what happens is when you increase P, there is a moment when you get what's called gigantic connected component, where majority of the nodes becoming connected. Now, if you think about this, what kind of structure you would expect to have in order to connect the largest number of nodes with the minimum number of edges? What kind of graph structure would that be? Okay, good. Well, no, wheel is not, it's going to be harder, but there is a structure that usually allows you, that, has like logarithmic properties, when you talk about, it's a tree structure, right? So tree usually with the smallest number of edges, minimum spanning tree. Have you heard about this? So what is minimum spanning tree? Минимальное остовое дерево. So it is the smallest number of edges, right, to connect all the nodes. That's what minimum spanning tree is. And there are algorithms to build it. So what happens here is at first you get connection that looks almost like a tree. Now, remember, this is a random graph, right? Which means you might, get sometimes cycles, and anytime you run the experiment, you'll get a little bit different result, right? But on average, that's what's happening. So you get from completely disconnected to fully connected, and you go through the phase transition. And what's interesting is to try to figure out at which density, at what moment in time, you will actually get those nodes connected. Like imagine that you do this experiment. You start with P equals 0, and everything is disconnected. And then you slowly increase the probability of any two nodes being connected, right? Kind of slowly increasing it. Again, we know that when it is equal to 1, they're all connected. Now you're slowly increasing it, and then there will be a moment when the most of the nodes becoming connected. So the question is, can we actually analytically find a moment, find this density when for the first time these nodes are connected? And, again, with this random graph theory, the answer is yes. And we're going to go through this formula. It's actually quite easy and quite interesting. So let's call U a fraction of nodes that do not belong to this gigantic connected component. Now, gigantic connected component is when the nodes getting connected, right, into one component. It's almost the entire graph. So, but, at some time, it's not all nodes that belong to this component, right? Actually, at the very beginning, the component is very small. So the probability that the node does not belong to this component, which means you cannot get from this nodes to any other nodes connected. So how do we calculate this probability? Well, you can actually think about it the following way. There are various options for this to happen. So one option, your node is isolated. So it's not connected to anybody. So of course it does not belong to any connected component. That's probability of the node is equal to 0, of node degree is equal to 0. That is isolated node. Or the node can have one neighbor, but this neighbor should not belong to this component. Then there's just two nodes connected, but they're not connected to the rest of the nodes. So that's an option P, probability K equal to 1, and its neighbor is not belonging to connected component. That's that's the fact, that's the U. So probability of node equal to 1 times the probability that the neighbor is not connected to anybody. Or the node can have two neighbors, but each of them is not connected to the component. That's the case where probability K equal to 2, and probability that neighbor is not connected is U squared because it's for each of them. Okay? Now, I'm putting here sums because it could be this way or this way or this way or this way, right? And so if you will calculate probabilities, you just add these things up. Well, you can just take this formula, add everything up. P of K, P from K, the function is, we know it's, right? It's Bernoulli distribution. Plug it in, see the formula. If you look at it carefully, you realize that e to the power minus lambda, you can pull it out from the sum, from under the sum. You get lambda to the power k uk divided by k factorial. But this is nothing more than e to the lambda u, right? It's exponent if you write it out in a series. Yeah?
Why sum is to infinity? Because we have only n.
Very good point. You actually, yeah. I mean, to be fair, you of course need to put here endpoints, right? But remember, we're talking about this. So we have this graph, and then we're trying to do this n go to infinity, where p goes to 0, as I mentioned before, to consider this continuous limit, right? To consider this limit, and we can use this distribution in this form instead of like original discrete. You can actually, what I'm trying to do here is, estimating. And so the right way to do this would say k from 0 to n, lim n goes to infinity, right? And then be very, very kind of accurate in how you do this. I'm not doing it, I'm just saying like, okay, let's just put here infinity and let's sum it up. But you're absolutely right. And by the way, you notice in all of those models, because you start with a sort of discrete story, when we talk about this Barbashi-Albert model next lecture, we'll also switch to like discrete limit to continuous to make certain calculations easier. But in fact, I mean, after this has been done, people went through it, did this very precise, very good, like solid computations. So it is possible this is just sort of approximation for us to get the feel of what's going on. So if you do this, you literally get an equation, u on the left-hand side, and exponent e to the power lambda u minus 1 on the right-hand side. Okay? It's an equation. Can we solve this? So first of all, I'll just simplify it a little bit. If u is a fraction of nodes that do not belong, 1 minus u is a fraction of nodes that does belong, right? So then you can write this equation. It's a little bit easier to write it. 1 minus s equal e to the power minus lambda s. So that's the equation we need to solve. If we solve it, S, so lambda, remember, lambda is average node degree, which is connected to our parameter P, to the density of the graph. So literally think about lambda as corresponds to the density of the graph. And S is a fraction of the nodes that belongs to the gigantic connected component. And when density is very large, all the nodes will belong to connected component. When density is very low, nobody belongs to connected component. And so S is this fraction, so it's between 0 and 1. Look at this equation. 1 minus S equal E to the power minus lambda S. Very, very simple equation. Can we solve it? Can you solve it analytically? Why not? Because, right? Yeah, exactly. It's very simple, but you cannot solve it analytically, actually. So you can solve it numerically, right? But we're not that much interested in a solution, in numerical solution of this. We're actually interested in a situation when, if we can figure out at which value of lambda, at which parameter lambda, this equation will have non-zero solution. So the zero solution, S equal to 0, it always exists, right? In this equation. So we're interested in non-zero solution, because non-zero solution, which means we got some fraction of nodes that are part of this gigantic connected component. And so the way to do it, and I think you probably have seen this type of approaches before, is to do it, graphically, like with pictures. So if you look at this equation, I just took that equation, rewrote it slightly. You got S on the left, 1 minus E minus lambda S on the right. So I can plot this, right? Y equal to S, this is diagonal, it's dotted line. Y equal to 1 minus E to the minus lambda S, it's this curve, right? And depending on the lambda, this curve, and on the picture it's actually called C parameter, but it's lambda. It can actually go either very low or it can go higher, higher, and higher, right? And depending on the lambda, right, depending on the slope, it might actually have non-zero solution or not have it, right? So here, the only time they intersect is right here. Then you increase the slope. Oh, there might be some intersection here. You increase the slope even more. That's where you have your non-zero solution. So if you look at this, can we think about this parameter lambda, right, that will distinguish the situation where you only have a zero solution and non-zero solution? That's a question. So what needs to happen to this red line for it to further?
Maybe derivative of 1 minus exponent should be equal to 1 in order to...
Yep. So the slope of this red curve at the origin should be higher than the slope of the dotted curve, right? Because then it will bend and cross it. If it is less, then it will, go below it and never cross it. Make sense? Okay. So then what we do is very simple. We just calculate the derivatives at the origin, right? The derivative of left-hand side is 1, like you said. And the derivative of the right-hand side, well, you differentiate it as lambda E minus lambda S. We calculate it at S equal to 0 because we need to do it at the origin. So it actually becomes lambda has to be greater than 1. So the critical situation, when you first start getting non-zero crossing, right, is when this lambda is equal to 1. So when lambda is less than 1, the only solution you have for this equation is the fraction S is 0. When lambda is greater than 1, or, first equal to 1 and then becoming greater, you get non-zero solution. Now, sort of unrolling back, to remind you, S is the fraction of the nodes that belong to a gigantic connected component, that are connected to each other. So that means that graph becoming connected when the parameter lambda crosses a value equal to 1. Okay, you're probably a little bit lost by now, but let me give you a very simple image and you might understand what's happened. Again, what's lambda? Lambda is p times n, which is average node degree. So what it says, that's this whole thing, the only message here is the following. When average node degree start exceeding 1, your graph becoming connected. So when on average your node has more than one neighbor, the whole thing gets connected. But that makes sense, right? Because if you have just one neighbor, it's hard to get the whole thing connected. But if you get a little bit more than one neighbor on average, right? It means for a guy, okay, there is a way to this guy and there is a way from this guy, so there is a chance for them to be connected. And so there is a critical point, which is the density p times n equal to 1, or average node degree is equal to 1. When you start getting connected nodes. In the homework, you will have this exercise when we're going to ask you to actually do this, right? And so you'll be able to, you'll just generate random graphs. You will increase the parameter, and you will see how at first they're disconnected, right? There is different disconnected parts. And then as you increase the parameter p, as you increase density of the graph, all of a sudden you will see that how whole thing becoming connected. And that's actually pretty cool. If you do this simulation, and that's like I did this simulation for, what is it? And I put like n, 10,000, and that's where you're growing. That's how you grow things. That's the size of the parameter. And what I did is I calculated the percentile of the nodes that are connected, right? So they form the connected component. So the way to do it is very easy, right? You run the function that's called connected component, and you take the largest, and you just calculate how many nodes are in that largest connected component. And so what happens, there are almost no nodes in this largest connected components at the beginning, then you're increasing, and then suddenly, when average node degree is 1, there is a very fast growth of this gigantic connected component. And when you get to like 3 or 4, average node degree, all the nodes are connected. Some of you that maybe had physics classes or remember physics classes, it's called phase transition, right? Phase transition of second kind. It's the same as freezing water. Properties stays the same. The temperature drops, nothing happens, right? But then it reaches 0, boom, and all of a sudden you get solid, right? It almost happens almost instantaneously. Maybe there is like, at first you get some sort of parts of ice, right? But then temperature changes a little bit more and all of a sudden everything is frozen, right? So it's a very fast change from different states. Here there are two different states. One state is a graph disconnected, another state is a graph connected. You have this gigantic connected component that takes over the entire graph. Hello? You still with me? Sort of? Kind of? Okay. So here is a few, yeah, you can barely see it. But here, is it me or it's like out of focus, like completely? Let's see, just a sec. No? Nothing changes or getting worse? Anyway. So what you see again here is on the horizontal axis, that's changing of average node degree in the graph, which is the density of the edges in the graph. On the vertical axis here is that fraction of the nodes that are in gigantic connected component. And the way, what you see here is this sort of simulation. This is the random graph that's been generated. Green nodes are just sort of all nodes, and the blue that belongs to those big components. And you notice how it progresses from left with only a few nodes connected to like many nodes connected to pretty much all node connected, right? So that's sort of the probably one of the coolest properties of this random graph, the fact that it has phase transition. Okay, I see you're not excited. Fine. And there are different regimes, right? There are regimes when, again, it's barely connected, then there is this critical point, and then there is like different supercritical regimes. And if you're interested, you can dive into formulas, and for each of those sort of for each of those inequations, you can actually estimate how many nodes are connected within that graph. So you can actually go through all those formulas easily. But there are a couple of things. And here is an example. If you look on the horizontal axis here in this table, so every column is just the size of the graph, and every row we have different level of the density. Again, the top one is average node degree 0.5. The next is average node degree is 1, average node degree is 2, average node degree is 4. And that's what those graphs looks like, right? So realize that when you go, when you look at the very top row, these are like sort of disconnected pieces. But when you go and look at the node degree equal to 1, average node degree equal to 1, or this parameter equal to 1, control parameter p times n, then getting trees-like structures, and then you start getting loops, and then graph is getting fully connected. So that's the progression. By the way, this is I think the software is called EDY, the one that's used to draw this picture. So if you want to be able to draw this type of graphs, that's the one you can use. Now, in fact, because this is such a precise mathematical model, you can actually investigate and find out a lot of interesting properties. So the behavior of this type of networks are kind of very well predictable. And in fact, you can observe how, and I'm not going to go into like sort of proofs of this, but you can observe how when you increase this density, you first get nodes, and what you see here, again, horizontal, left to right, is increase of the density of the graph, right? Increase of average node degree. And what you see is when the density is low, you of course have separate single nodes, but then they become connected into pairs, but then you start getting trees. And then, for example, when at the level of p proportional to n, you start getting cycles of different degrees, and then you're getting denser and denser and denser. So in fact, for this type of model, when you change p, you can predict for every p what type of these little structures you will see, whether you see trees, whether you see cycles, or whether you see more sort of denser figures, right? So this model is like completely predictable and calculatable. Couple more things. Now, we talked about the node degree distribution, right? And we figured out that, well, unfortunately, node degree distribution is, not power law. It is, Bernoulli, right? It's Poisson distribution. Let's talk about two other parameters, right? We talked about clustering and clustering and small world phenomenon. In terms of clustering, well, again, clustering coefficient is really, it's about the existence of triangles. Or it is about the probability that if this node has two connections, right, that those guys are connected between each other. That's what clustering coefficient is, right? It's a probability that two nodes that have common neighbor connected between themselves. Well, in this model, it really doesn't matter if the nodes have common neighbor or not. The probability that they're connected is p, always, because that's the way we build the model. And so, and clustering coefficient, which is calculated again as if you look at the node and look at its neighbors, and we say how many actually connected out of the total possible connections of your neighbors, total possible connections of a node neighbors is k times k minus 1 over 2, because, for a node degree k minus 1 neighbors, this is how many triangles you can form. On the top, it is a probability that each pair connected times the number of pairs. Of course, kk minus 1 over 2 cancels, so it's just p. But again, it's sort of obvious because it doesn't matter in this model if your neighbors are connected or not. The probability that two nodes are connected is just p. That really tells you that this clustering coefficient here depends on the density, depends on average node degree. And so if node degree, say we have fixed and we have a graph that's becoming bigger and bigger, the clustering coefficient goes to 0. In plain language, it really means that there are few triangles in this graph. So it means that with this type of graph, with this type of model, you will not have a lot of triangles, and clustering coefficient is very small. Now, that means also that this is not the model that would describe social networks, because in social networks, that's always the case, yes.
Cluster is a triangle?
Yes.
And that's the definition of cluster.
We're going to talk about it a little bit more. There is a sort of collision of terminology. When we talk about, we'll talk later on in the lecture about clusters or communities in the graph. By that, we understand the group of nodes that are tightly connected to each other, and that's what forms a cluster. The same way is in data mining definitions, right? And that's also called network community. Here, unfortunately, it also carries the name of clustering coefficient. We're not talking about clusters, we're talking about clustering coefficient, which is in fact just literally the number of triangles in the graph. We're going to talk a little bit more about like different flavors of this coefficient. But that's not, again, it's not clusters, it's clustering coefficient. The other name for it is transitivity. Again, the chance that two nodes are connected if they're connected to the same node that they're connected among themselves. Does it make sense? Yeah, so unfortunately, again, this is just collision in naming. So it's not cluster, it's clustering coefficient. Okay? All right. Graph diameter. Now, graph diameter, we actually did this exercise last time. This is a very simple exercise. You notice that just when the phase transition happens, right, the graph looks more or less like a tree. And so if you had, tree kind of structure, again, for those who remember a little bit of discrete math, when you have tree kind of structure, all the sort of distances along the trees is always going to be logarithm of number of nodes in the tree, right? That's the whole point of having tree structure, is to be able to reach any node in logarithm number of steps, if there are n nodes in the tree. And so this is very simple sort of, again, not precise calculation, but saying that, look, if you have a tree, and let's say we take, on average, we want to calculate how many nodes are d steps away from a particular node, and if k is a node degree and k average is an average node degree, we pick up a node, and let's calculate how many nodes are on average d steps away from a node if it has on average k neighbors. Well, it's k plus k squared plus k cubed, etc., just each and every layer, right, around the node. We did this exercise last time. You add this up, of course, it's k to the power d, and so that means, if we calculate d steps away, well, the diameter, or right, the maximum diameter here in this is logarithm m divided by logarithm of k. So in terms of short distances in the random graph, yes, they're short. And short meaning logarithm of number of nodes. Again, remember last time we talked about, the possibility of a grid, and if you have a grid, things connected on the grid, right? Then the distances, and there are n nodes in this grid, the distances will be order of n, right? Somebody corrected me, yes, correctly, that if you think about them, just a lattice, a grid, two-dimensional, n step, there are two n steps to get from one corner to another, but it's order of n, right? And here the point is, yes, you have n nodes, but on average, the distance is logarithm of n, which makes it a huge difference, right? When n is small, who cares? But when n is, 10 million, there is a big difference, whether it's 10 million steps to get from one part to another, or it is, just 7 steps, which is logarithm of, 10 million. So, that's very critical. It just tells you that, even if connections form randomly, you can still have this very, very short path, which kind of sort of, might explain this 6-degree separation story. But again, guys, this is a model, right? So it does not claim to precisely describe the world. It just says, look, we make this assumption. We generated some graph out of this assumption. This is the property of this graph. Now we can, twist and tweak parameters. Let's use this model to build maybe something more, more complicated but closer to the reality. But this is the instrument, right? So it's not supposed to precisely reproduce reality. Okay, just to sum up, for this random graph model, so no degree distribution is Poisson function, right? It has, this sort of bell-shaped story, which is not the way the real world is. Average path length is actually short. It's logarithmic of number of nodes, which is, close to real world networks. Clustering coefficient can be actually very, very small. It's again goes from average node degree divided by number of n can be large. So this is not what we typically see in real world networks. So as is, random graph model is not directly applicable to real world networks, but it's a good instrument to study the behavior and to actually try to build more complicated models on top of it. So this is a picture, I showed it last time. It's logarithmic scale. What you see, the purple lines here are, remember, for power law distribution, the degree distribution, power law degree distribution, if you go and use logarithmic scale, it's going to be a straight line, right? And so what you see here, internet, like science collaborations and protein interactions, they all more or less fit a straight line here on this graph. And what's in green, like yellowish greenish, this is the same. We take the same average node degree, but then we generate a graph based on the random graph model, and that's the degree distribution you would get, right? So it's logarithmic scale. Obviously it doesn't match the real graph, but this is just for comparison. Now, can we correct that? Yeah, of course we can. I mean, and that goes into okay, let's make model more complicated, right? Because the previous model was just beautifully simple. Take any pair of nodes, right? Probability P connected, not, that's it. We can make things much more complicated, but then we can force certain degree distribution that we want. One example is you can actually construct a random graph with a given node degree sequence. So let's say I want a particular sequence of node degrees, right? I want nodes with degree 1, 1, with degree 2, with degree 3, with degree 5, 5 nodes with degree 5, 7 nodes with degree 11, etc. Can I build a graph that way? Well, yes, if you provide the right number of edges, and then you can actually add randomness to this construction and build this type of graph. Now, in the simplest scenario would be the following. Think about it this way. Let's say I have this n nodes and I have given degrees. So which means I pretty much have those nodes that are aligned here. And what you see, it's called a stub. It's a part of the edge, right? If you connect two nodes, those two stubs become an edge. So it's literally just a visualization of a node degrees, right? So I have two nodes with degree 1. I have one node with degree 2. I have one node with degree 3. I have two nodes with degree 4, one node with degree 5. And I'm just trying to see if I can make a graph out of it, of course, with that m number of edges. And interestingly enough, if you actually, you can actually force it to happen by, again, randomly matching those stubs. And that if you calculate the probability that two nodes are connected, it will be the following. It will be node degree 1 times node degree 1, node degree 2 divided by 2m minus 1. Why? Well, because the total number of connections is possible 2m minus 1. And or if you put m in there, it's the sum of all all possible degree. So what happens is the following: you take an edge, you take a node, and the edge can connect to any other stub, that is available to you. Now, there are ki ways for a given stub. If its node degree is ki, there are ki ways to select this stub. And for other node, there are kj ways to land on it. And so that's where this product comes from. Now, the only question is, if you take a power law distribution, can you generate a sequence of nodes that follows this distribution? Yeah, you can. So you can actually force the distribution to be power law, and you can create the graph. Now, if you just do it that way, the simplest way I described, you might get self-loops, because nowhere in this process I say you cannot connect to each other, and you get multiple, you can get multiple parallel edges, which means two nodes can be connected with, with, let's say, two edges, right? Instead of one edge. But that's like the simplest sort of approach. It's called configuration model. There are many more models you can build out of this type of approaches, right? Where you can actually force the distribution, and get the distribution you want and get some randomness into it. And sometimes this is actually a good, what's called null model. So the idea is, if you want to see if your graph has certain properties, it's always helpful to compare it against something, right? But comparing it against some sort of absolutely random graph, might not make sense. So what you can, for example, do is you can take your graph that's given to you, and then based on those node degrees that you do have in this graph, build a random graph, which means you will have the same nodes with the same degrees, but they will be connected like randomly. So you want to compare apples to apples. So again, you have like a real graph, and then you take another graph, which is your real graph, but you connect things randomly. So you throw randomly edges. And then you'll have two graphs with exactly the same degree distribution, with exactly the same number of nodes, exactly the same number of edges, but different connectivity patterns. And then you can see, okay, if one connectivity pattern is random, you just generated it, and the other one is your graph. And then you can, for example, compare it, like it's literally going to be a baseline, and you're going to compare it against this graph and say, oh, yes, there is some structure, there is some patterns I see now, compared to random. In some sense. Yep. So, okay. So that's pretty much it for random graphs. We're going to have a break now. If you're interested in pure and beautiful math, go to this paper, 1959. It's actually a pretty readable paper, but it's long and has a lot of calculations. Actually, it's a sequence of papers by Paul Erdős that I would recommend you to read through. Okay, let's have a 10 minutes break, and then we come back and have another lecture on small world and Barabashi-Albert model. All right? Try not to fall asleep. Let's do part 2. We're going to talk about 2 more models, different models. This is sort of more contemporary models that have been created because this random graph model, doesn't exactly describe what's happening in the real life, and so people try to actually come up with slightly different, approaches and see if we can get closer to reality, but at the same time, keep life still simple. So, if you think about this, and this random graph model, right? We just talked about it. This notion of you have fixed number of nodes, and that's the way connections form, right? Maybe this, if you think about like any, real life process, maybe this kind of reflects the way, for example, people meet at the party, right? Like, let's think about this. Let's say you come to the party, you don't know anybody, you do not know anybody, right? You mingle around, you find somebody to talk to, right? You talk for a few minutes, so that's your edge, right? then what do? Well, you get bored of this person, or the person gets bored of you. You excuse, you go grab a, I need to go grab a drink or whatever. You just sort of disappear, right? Then you find some other victim and, spend some time. And that's how connections form, right? Now, interestingly enough, if you try to make this social experiment and you actually, for example, try to spread rumor through this, which is, let a few people know, I don't know, that there's some great wine, like there is like 5 bottles of wine, but one of them is like the most expensive, for example, right? Eventually, like the entire room will know about it. How that happens? Well, because with a certain number of edges, you'll get connected component, which means any rumor will propagate from one person to another. Eventually, everybody will know it, right? Now, that's how rumors like literally spread. This model might actually work in some sense. There is some reflection to real life. Now, but let's think about now slightly different story. Let's think about, let's say, Facebook or any other social network. If I try, why would the random graph model, why it does not reflect the structure of social network? It does not reflect the structure of the web or the structure of, Facebook or any other social network. What's missing in here? What's actually happening usually on Facebook, and what's missing in the model? I mean, Facebook is not built the way we kind of communicate, at the party, the way I described. Actually, there is another, there might be also a mechanism in the party that is slightly different from what I've been describing, right? I've been describing the situation where, you kind of come to the party, right? You don't know anybody. You just pick up a random person, or person picks you up and, you talk. But on the other hand, what also very often happens at the party?
Your friends.
Okay, there are friends, but there is...
Friends, there's a person you don't know, so you become a friend.
Okay, you come to, you see your friend talking to somebody, you come there. Now, also, think about this. 2 situations. There is this, lonely guy standing there, and then there is somebody who is surrounded by a lot of people talking to him. Where do you go? To a lot of people, right? Nobody likes losers. You're going to go to where the action is, right? Now, the random graph model does not actually take this into account. It actually says, all the pairs possible. And what we're saying is, money goes to money, right? You see somebody popular, you go join that. Now, if you think about like Facebook or any, I don't know, Instagram or anything else, you're going to follow the popular account. You're most likely not going to follow like sort of random. And you prefer, popular person to kind of obscure person. That's one situation. So, in fact, in the name, in the model, there's a name for this. They call it preferential attachment. So you prefer it, so, you have certain preferences. You're not just going to randomly, attach or connect to somebody, right? You're going to choose who to connect, and, in the case of graph, you might want to connect to a person who has a lot more people, talking to him, which in the language of graphs, what does it mean? Prefer to connect to who? To a node with a high degree, right? With a high degree. So you do not randomly form connections, you pick up nodes with a high degree. So that's one situation. There is another something which is very typical in the real situation in the real life and the Facebook, etc., which is not reflected in random graph model. Well, in fact, random graph model postulates the opposite. Think about the party. What's usually happening? It starts with, 2, 3 people, and then what? As time goes by, more people come. What happens with, Facebook graph? It grows with time, right? Like any social network, it starts with a few people, and then it's growing. The same thing with the web, right? Started with a few pages, more and more people created pages, things getting connected. So there is a growth mechanism. And in random graph, it's not reflected. In random graph, we just said, okay, we have n nodes, we have probability of connections, boom, things got connected. So the random graph model, in some sense, misses a few things. It misses this preferential attachment, which is very typical for our social lives, and it misses the growth. Now, it actually can misses a lot of other things, but these are like jumps at you if you especially want to model social networks, right? It's hard to explain this preferential attachment if I'm talking about, I don't know, the road map, right? Or anything of that kind of like those sort of technological networks, mechanical networks. But with social networks, it's kind of reasonable, right? That coming to the party, you will join, the fun group, and not just as somebody, standing alone. Okay, so what you can do is we can actually we learned from this random graph model. We kind of know like what happens, how to simulate like random behavior. Let's just enhance it with those ideas, right? And that's going to be this preferential attachment model. In fact, I just described the whole model, by the way. Okay, that's what we talked already about. Yeah, so again, most of the networks we deal with, they evolve in time, right? So there's new nodes, citation, web, social networks. So that was the idea that Barabashi and his student, I think postdoc, I forgot, they came with in 1999. It's called a dynamic or dynamical growth model. And the idea is the following. I need to formalize this right now, right? So we just had motivations. Now we need to formalize this to make it a model. So first of all, we start at time equals 0 with n0 nodes. And they might be connected, might be not connected, okay? So it's a party with like a few people, might be talking, maybe not talking, right? Then we force a growth function onto this. At each time step, there is a new person arrives, right? Or there is a new node arrives, and it instantly forms m edges. M can be equal to 1, can be equal to 2, 3, whatever, right? Maybe somebody can talk simultaneously to a few people, different people, or maybe just to one person. So you have this few initial nodes, then you get a new node that comes with several edges, and it connects to available nodes, right? Then the next node comes, the next time step, with the same number of new edges, free edges, and connects to available nodes. Then the next one comes and connects to it. Make sense? It's growth. So every time, on every time step, you get a new node coming in, and this new node brings in m edges, m connections. And then the question is, when you get this m connections, where are they going to be connected to? And then the idea of this preferential attachments. Its connection is a random, but the probability is skewed such a way that the probability connecting to the higher degree node is higher, or just plainly proportional to the degree of that node. So the probability of connecting to the node degree 1 is the smallest. The probability of connecting to the node degree ki, degree k, is k, proportional to k. And it's normalized by the sum of all the node degrees in the graph. Okay? So the process is, you get a new node, has m edges. Every edge is getting connected to a node proportionate to the node degree. Now, the important part here, it's still a random process, right? So when the node comes in, it still can get connected to a low degree node, not to the highest degree node, but with much lower probability. Yeah?
How we choose m?
M is the parameter of the model. The only thing which is needed in this model is that you need, on the first step, you need to have at least m nodes available to get connected to.
Okay, so each node comes with
m edges. Yes. And that's, again, guys, there is no ultimate truth in here. These guys came up with this model, right? They postulated that's how it's going to be. You can create your model and say, hey, in my model, the first node will come with m edges, the second with m plus 1, the third with m plus 2, or you can say, and then we're going to name it your model, right? I think this model became very popular because it's actually, again, very simple. It gives the right distribution, right? And people just start copying it and, modifying it. And there's like bazillions of models right now built out of this one. But, this kind of became a reference model. And this paper is cited, like insane number of times. It's been published in Nature and became very, very popular. Pretty much guys made a career out of this paper. So anyway, so there is two factors, right? Growth and preferential attachment. And that's what makes this model. Let's just try to investigate it. Now, in this model, there are certain things we can also calculate using approximations. But it is actually less predictable than random graph. So it's going from the sort of mathematically pure models where you can do a lot of things analytically to this more models where people kind of create a model, but then to calculate the properties of the model, you actually simulate this graph, you build the graph, and then you just measure it. So you cannot analytically calculate things. The more complicated model is, the more complex model is. So here is an example of how you build patterns here using this this approach. Let's say you have this 3 nodes connected by edges, then you get a new node, the white one, right? It gets connected to those 2 nodes. If you go left to right, times increases, the size of the node here is proportional to its degree. And so every node coming into, and the new node is white, and every node coming into, it has their higher chances connecting to the larger nodes, like nodes with a larger degree, right? But it's still a random process. It can connect to some other node. But notice what happens. If you think about this and think about this process, even in a party setting, right? There might be 2 groups that formed. They're not like very big, right? And then there's sort of single people mingling around. And then, but as people come and they start preferring to joining these groups, right? The groups become disproportionately large, right? They start dominating. And that's exactly what's happening in this model, right? It is the same story as, again, money goes to money, right? You got some money, you get more and more and more and more. And so that's what happens here. And notice, compared to random network, you get nodes here with actually a very large node degree. Nodes like everybody wants to get connected to. And then, the minimum node degree here is for every node, however edges it brought in with them, like m edges, that will be the minimal degree in this model. If it is m equal to 1, well, it will be degree 1. If it's m equal to 3, it's going to be 3, etc. Okay? Make sense? See how it works? Okay. Now, with this model, we still can do certain calculations. Again, you're going to do this sort of, we're going to try to dance in between, like, pretty strict calculations and sort of relaxing things and think about a continuous limit where we can, instead of summation, look into integration and try to differentiate things. So the idea is the following. Let's look at the time evolution of a node degree. If at moment time t, the node degree was ki, we want to see what's the node degree is going to be at moment t plus delta t. And during this delta t, we get new nodes coming in and connecting. And then the probability of connecting to the node of degree ki is proportional to the node degree, right? Normalized by sum of all other node degrees. And if I want to calculate, this is the probability of connecting, and every time a new node comes in, it brings in m edges, right? Now, in this model, you can actually, it could happen that you get parallel edges, that some of them will connect to the same node. Anyway, so node degree at time t equal plus 1 is at time t plus delta t, or time t plus 1 is a node degree at previous time plus the probability of the new coming node to get connected to you and bring in m edges. That's pretty much it, right? It's as simple as that. Then you can plug in all those things, and you get very simple differential equation. dk dt is mk divided by 2mt, right? Ki is a node degree of node I, and then you just integrate this. And if you do it, what you get is that the degree of the node grows at the square root of time. The ratio of time divided by number I. Now, in this model, what's interesting is there's interplay in between time and the number of the node, because remember, every node appears in each moment of time. So number I means that the node appeared at the moment of time I, right? So I and time in the same units. If I try to draw this, this function, yeah, that's what it looks like. So it's very simple. T is growing. You have your square root, and red node appeared at moment of time, I don't know, 30, right? The blue node at 20, and the green node appeared at moment 10. And then when you look at how they grow with time, their degree, well, that's the lines, right? Now, this is actually a very sad picture. Why is it a sad picture? Well, because it actually tells you within this model that there is absolute first-comer advantage, meaning the earlier you join the network, right, the higher your node degree will be, and nobody else who joined later can reach your scale. Well, I mean, of course, life is more complicated, right? But if we were following this model, right, then anybody who, I don't know, started making a certain amount of money and had a certain amount of money more than you at some moment, you will never be able to catch up. Because according to this model, if everybody lives by the same process, right, there is no way to catch up. Okay? So that also means, yeah, that the sooner you join a social network, the more friends you're going to have there if the friendship is determined by the same process, right? It also tells you that, the earlier you come to the party, the bigger chance that you'll have, bigger crowd around you, and the crowd will, anybody who comes later, if he has the same attractiveness power, right, then he will not be able to beat you, right? So that's sort of the essence of this preferential attachment. Does make sense, picture? Okay. I mean, again, the bottom line is, yeah, the node degree growing with time, right? And the earlier you grow, I mean, the earlier you join, the higher your node degree is going to be. Pretty much that means, if you try to build, and this is a model, this is a network built by Barabashi-Albert model with m equal to 1. So every time new node comes in, it just have one edge to contribute. And then it looks like, like a tree-like structure. And what you should note is that and it's numbered here by its number I when the node joins the network, right? So it's a time moment when the node joins, and it's a sort of node number. And so you would see that the numbers, like smaller numbers, they're close to the center, right? Here in the center is number 2, and you realize that's sort of the pattern, right? The small number is the closest to the center. But remember, this is random, still random process. So, nothing prohibits, number 70 to connect to the guy, who has number 2, right? There's no problem here. But overall, that's how it's going to be forming. Yeah.
How it happens that node 11
Mm-hmm.
be 2 and 4?
It's not between, there is like 2 edges between 11 and 2.
Yeah, there was, I think there was like double edges there. And again, it's a random model, right? So, I mean, it's always probabilistic. So there are certain things that are, there is probability of anything happening here, right? But in this particular case, you're absolutely right. It is because of double edges there. But you can see like the node number 70 or 99 is connected to 2, right? So you would sort of expect, yeah, you would like, but number 2 is actually, we don't see it because, edges overlap, but the degree of number 2 is much higher than the degree of any other nodes. And so any new node coming in will have a higher chance connecting to node number 2, right? Okay, again, guys, this is within network X, there is this generator for this network, so you can play with it easily. Okay, now this is kind of an important graph. I'm sorry, important formulas. I'll try to explain it hand waving, but so now we know how the node degree evolves as a function of time. What we eventually want to have is a probability distribution function. So you want to have the distribution, which is a probability of a node having, a certain degree, which is, if I take a snapshot of this graph at some moment of time, I want to know how many nodes of degree 1, how many nodes of degree 2, how many nodes of degree 3, or 4, or 5, et cetera, right? And I can measure this at any moment of time. And I want to have this distribution, right? So I want to make sure, or at least check whether it's like this, bell-shaped like or any other. So, well, how can I do this? Well, the trick is the following. And I wish I had a picture here. So the trick is the following. Every node, it appears like node ki appears at the moment of time I, right? So by taking this function time evolution of node degree, I can see that the nodes that they have, if I want a node to have a degree less than given, they should appear in time later than a certain amount of time, later than a certain moment. Make sense? Look, the degree of a node grows with time. So if I want to pick up the nodes that are less than a certain degree, they should not be living within the graph for a long time, because the longer they stay, the higher their degree, because their degree grows with time. I here is a node number, but it's also a timestamp when the node appeared in the network. So I is equal to 1, it's the first node, it appears at the moment of time equal to 1. I is equal to 2, it's the second node, it appears at the time equal, to 2 seconds. I equal to 3, it's the third node, and it appeared in this network at moment 3. Right? So that's why we can actually do the ratio, T over I, because otherwise, physically it wouldn't make any sense, right? So, all right, guys, are you with me? So this notion that if you want to select nodes that have low node degree, you need to look at the latest arrivals. Because those who arrived earlier, they already grew up their degrees because the new nodes coming in connected to them. So it's the latest arrivals that will have low node degrees. Make sense? Again, the way it's built, you have a node, new node comes in, right, with a degree 3, let's say three connections. This guy who was there, his degree increases. New node come in, this guy's degrees increases, this still has degree 3. New node comes in, his degree 3, everybody else who was before him, their degree increases because he connects to them. So if I want to select nodes that have low degrees, they will be in this like latest arrivals. Newest nodes. Okay? Make sense? Okay, that's what it says. It says, if I want to select nodes with degree less than k, their arrival number, I, should be greater than that thing. Okay, that's the notion. And then, the only thing I want to do is, now if I know which nodes have low degree, I can say, well, I want to calculate probability of randomly selected node to have a degree less than k. It is all those nodes that arrived after that moment of time I. Because they all will have a degree less than given. Because their degree grows with time, and so they just survived they lived in my network smaller than a certain amount of time, so their degree could not be greater than k. Hello? Kind of feeling it? No? Sort of? Kind of? I recommend you do this. Sort of draw a timeline and just think about this, where nodes arrived and like, where is the moment of time I and etc. Yeah.
It's actually possible that, for example, first node in this office could be this degree.
It is, except for it's a very, very, very low probability, right?
This formula is true because of uniform distribution points on time.
On the timeline, exactly.
And okay.
Because we get a new node every time we get a new node. At second 1, at second 2, at second 3, at second 4, at second 5, we get a new node. And so what's okay? Okay. So again, imagine timeline. And every time step, you get a new node coming in, right? And sort of, these are old nodes, and these are new nodes. And so degrees of the nodes are getting proportionally higher than old nodes, like the highest degree, because remember, node degree grows as a function of time, as a square root of time, right? That's where they get. And, these are the newcomers. And what I'm saying is, in order to calculate the probability of a node to have a degree less than k, I need to look at the latest arrivals. Okay? And how many of them, that's just sort of what comes from the formula. And so what says f of k is I'm just saying the total number of nodes n0 plus t. N0, it's initial number of nodes. There has been t steps, so you add t nodes. So n0 plus t is the total number of nodes. This m squared t divided by k squared is this, it comes from that formula, and I normalize by n0 plus t. And so this is probability of selecting a node to have degree k less than k. And so if I want to do distribution function, I need to just differentiate this. Differentiate it, get 2m squared divided by k cubed. Which is actually, of course we tricked this model into doing it, to becoming that way. But the answer by itself is kind of, very nice to the power law story, because it says the probability of a node degree in this model of a node to having degree k is inversely proportional to that node degree to the third power. So if you remember power law, we said it is like k to the minus, alpha or minus gamma. Well, gamma here is equal to 3. So we got a pure power law in here. And that's what made this model sort of famous, because, look, there is this very, very simple process, preferential attachment, and if you follow through the math, it actually gives you the power law. Okay? Again, there's 1.5 formula here, but it takes some sort of thinking to understand how it all gets together. So suggest, draw a timeline, put dots there, like every second, and think what it means here for a node to arrive, and for how time goes by and what those i's mean in here. So this is just an example. Yeah. So the red line is Barabasi-Albert distribution, and the blue line is a random graph distribution. So it's very different distributions. Barabasi-Albert model gives us beautiful power law. Okay, cool. And this is the same thing in logarithmic scale, just to show you. Again, that, here it's a power law red, random graph blue. If I take log, well, power law, of course, is going to be straight line. The random distribution will look like that. Okay? This is something visually. Which one do you think is the random graph and which one is a power law? Which one? Yep. Why? Because of structure, right? Because you do have some disproportionately large number, large nodes. And you'll notice that, right? It's noticeable. Here is the result of the preferential attachment model run with m equal to 1, m equal to 2, m equal to 3. M is a sort of number of edges that the node brings in when it is connected. Okay, now, let's say, as I mentioned, this was like sort of the very first, attempt, right? And then of course there's like bazillion of models has been generated after this, sort of based out of this idea. One of them would say, okay, we added those two major properties, the growth and the preferential attachment. We can actually manually like turn off some of those properties. We can say, okay, you know what? Instead of doing uniformly at random, instead of having preferential attachment, which means, coming to the bigger crowd, right? Or joining a node, connecting to the node with a larger node degree. Let's say, it's uniformly. Let's say the network is growing, right? We get more and more nodes with time, but every newcomer brings m edges, but connects randomly, uniformly at random, right? Without any preferred connection pattern. What's going to be happening to, the distribution function? What's going to be happening to the model? Well, you can actually calculate instantly that node degree grows like logarithmically, and the node degree distribution has an exponential function, is following exponential function instead of following power law. Okay, fine, big deal. It's just saying like, to get the power law, you need to have growth, and you need both growth and preferential attachment. Like without one of them, you're not going to get the power law. You're going to get, different growth. You're going to get slower growth for node degrees. Over there it was square root, here it's logarithm, right? Much smaller, much slower growth. Again, the notion is this power law or preferential attachment guarantees very fast growth to large nodes. Versus this is more sort of uniform. Yeah.
What's the difference between this model and random graph?
Oh, it's growing in random graph with fixed number of nodes that are available in the system. And here, and we have this probability thing. And here we bring for every, we're increasing number of nodes, and for every node we bring certain number of edges. As you can imagine, you can come up with a bazillion more of different approaches here, right? You can say, okay, well, let's say, it's growing, but let's say some people leave party. Let's say, some people become friends and some people, break up friendship. I mean, you can think about very, very many ways you can modify this type of models and play with them. Now, yeah.
If you compare it to reality, here we have power law, but with only like 50 degrees, it's times 3. But we discussed that in real world, this parameter is more or other 3 is always 3.
2 and 2 and 3. What between 2 and 3? Between 2 and 3, yeah. So that's why they were very happy that it is 3, because yes, and if you remember, if it is below 2, then the fluctuations are very large, right? The integrals diverge, and when it's 3, your integral, 1 over, what is it? 1 over x, because it's 3, it's like 1 over k cubed, right? So which means average will converge, and the only problem will be with k squared, right? Because it's 1 over k, then it is logarithm, but that's just on the edge. If it is 3.1, for example, it's also converging. So 3 is a good number for the models. Okay, what we have here now with the power law distribution, we can calculate. With Barbash-Albert model, we were able to calculate the distribution function. Now with you can actually estimate average path lengths. There is this analytical way to do it. We're not going to talk about it, how they done it, but it's logarithmic. So this power law graph, as we saw, will create a small world. But the clustering coefficient, you cannot easily calculate, or this transitivity, or like number of triangles in this model. There's numerical simulations. It behaves that way with the number of nodes. So it's kind of also not very realistic. So again, this is a simplified version of reality. There's a model. This is the properties of the model. You can like it, you don't like it, but that's sort of the way model is. Now, there are probably bazillion of students, master degree thesis, and tons of PhDs that have been defended on the topics of like modifying this model, right? I mean, that's a very fruitful thing, right? You take a model and then you just make certain changes, and then there you go, you publish it. So at least there are several things that are kind of now known, and probably there are many more things that just people created, and by whatever reason. So one is this nonlinear preferential attachment, which is instead of just probability being proportional to the node degree, let's make it proportional to the node degree to some power. Nonlinear, something, right? K squared, or maybe K cubed, or maybe, I don't know, square root of K. Why not? Can you do it? Yeah, of course. Especially if maybe you'll not be able to analytically calculate everything through, but you can definitely put their parameter and do numerical simulations. Just come up with a reason why, your probability of attachment is not proportional to the node degree, but proportional to the square node degree. I don't know, but maybe, who knows? Link selection model, this is a different model. Here, instead of when the new node comes in, instead of connecting to the nodes with the highest degree, it randomly picks up an edge in the graph and connects to one of the nodes that this edge is connected to. Surprisingly, this model will also create this preferential attachment approach because, you're most likely to get an edge that connects to the high degree nodes. Then there is another model, which is a copying model, that it follows the following idea, that the node comes in, that it randomly pick up another node, and then it either connects to that node or copies one of that node connections. That idea came from like WebGraph, where when somebody creates a web page, it sometimes connects to some other page, or sometimes just copies links from that page, right? It says, oh, this guy points to those sites, let me also point to those sites, right? Cost optimization model, that's more of economics models where you can actually try to build a graph optimizing cost of communication between nodes. So you kind of inject yourself into the network in a smart way, saying, let's say, okay, who should I connect to minimize my cost of communicating with everybody in the room, right? So do I need to come to the host of the party? Do I need to come to the guy who is like mostly, has a bigger crowd around him? I don't know, but that's sort of the approach, right? And so you can come up with like lots and lots and lots of approaches, as long as you kind of set up this model structure where on every time step you add something, right? You can create your own model. You can name it the way you want to name it. You can calculate its properties, then you can publish, and then just see if people like it or not. Now, of course, it's going to be beneficial if your model describes something or has some sort of physical roots in the real life, and you can explain why you do it the way you do. But nobody prevents you from just coming up with anything you want. Mm-hmm.
Why nobody research model like preferential attachment, but every node comes with geometrically distributed number of edges?
Yep.
It's kind of natural model.
Maybe somebody had done it. So I would recommend Google it and see maybe it exists. It just happened, historically that these are the models that became popular, but there is no reason why not, what you're saying. In fact, this whole notion of preferential attachments, though today, like, the Barbash-Albert team kind of claims the fame of, building this model, putting this model together, publishing it, and creating all this stir and all those followers, right? In fact, this idea of preferential attachment, or like money goes to money, goes back to 1923. It's the famous Pola-Orn model. If you're interested, Google it. It's the same notion of actually adding to the urn with more particular type of balls. Then there is yield process. Then there is Herbert Simon famous paper on distribution of wealth, which is power law, which is again this sort of money comes to money. Then there is citation network 76. Then there is, so these guys were long down the long list of papers. Of course, nobody knows today if they came up with their idea independently or if they knew these sources. But, the story of preferential attachment, the way we call it now, it wasn't called that way before, but, it goes back to at least 100 years, right? So, now, one last model. This is going to be very quick. This is a different model where guys were thinking like, you know, yeah, a random graph model is actually not that bad, especially if we can adjust sort of distribution, power law, you know, the distribution function for node degrees. But there is this thing with triangulation, right? There is this thing with, you know, with the fact that in random graphs you don't have these triangles, right? In the social networks we do have them. So, you know, might not work, but let's try to come up with something very, very simple, but it satisfies, you know, pretty much all our properties, and then we'll think about, you know, why we do it that way. And so the idea is the following. Oh, by the way, and these guys are physicists, so they like to look at to study objects, or like if it's a graph or network, you know, without boundary conditions, right? So you kind of you connect this into the nice circle. But the point is, let's look at this network. Something like very, very artificial, but if you notice, these are triangles, right? Everywhere there are triangles. So the clustering coefficient is very large. It's 1/2. So it pretty much means that for every node, half of its neighbors are connected among them, right? So you take a node, you take its neighbors, half of them connected to each other, right? Now, the problem with this graph, if you want to travel from one end of this graph to another, you pretty much need to go through all the nodes, right? I mean, well, half of the nodes. And so the diameter is very large. So it kind of, you know, this graph, we artificially created it. It has very large clustering coefficient, but it doesn't have this small diameter. So how can we more or less preserve this large clustering, right? So preserve this local structure of triangles, but at the same time being able to quickly get from one part of the graph to another. What modification can be made? Yeah, we can just add a few like long-range connections, right? Pick up a few nodes here, connect it far away. And the second you do it, right, what's going to be happening is you can traverse locally to get to some node that it is, you know, long-range connected, then you jump across, and then you locally get to another node. Sort of pretty much like transportation today works, right? You take a car to the airport, then you go long distance, and then you take car to, like, you know, your final destination. And all of a sudden, you know, it's a small world, right? Driving a car will take forever, but as a plane, you're kind of having this long. And so there's only thought here, the only option would be like, okay, what we can do, we can either connect them, just add edges. But if we add edges, we're kind of, you know, modifying graph in terms of like adding edges, right? If we want to keep the same number of edges, what we can do is we can just, for example, disconnect, you know, two nodes, get this edge going from one node to another local node, and, for example, disconnect it and connect it to somebody far away. Then you keep the number of edges, you get long-range connections, you break a little bit local triangles, but that's fine as long as you don't break a lot of them. Make sense? Okay. So that pretty much was the idea. That's what Watson Strogatz came with. And it's a single parameter. This parameter is actually this probability of forming a long-range connection. We start with a regular lattice with n nodes, k edges per vertex, and randomly connect with other nodes with probability p. So you have these long-distance connections. Now, this p is different from random graph model. They just happen to call it the same way. But the idea in this case is p is equal to 0. It's a regular lattice, your original lattice, your triangles. And p is equal to 1. You completely rewired it, and, you know, only have like long-range connections, random, literally you create a random graph. And so somewhere in between the 0 and 1, there's probably a place where you have good properties, which is you still have long-range connections, so it is a small world, but at the same time, you do have plenty of enough triangles to have this, on average, on average, high connectivity and high transitivity clustering coefficient. So that's the sort of their idea. Increasing randomness, go from this very regular, and again, this is sort of, you know, if you notice this strange shape, But the point is, if you look at the nodes, you realize that the neighbors are connected, the neighbors are connected. So instead of this shape, you go, disconnect some of them, create long-range connections, you get your small world. If you disconnect and you reconnect all of them, you get a random graph. So somewhere in between, you hopefully get, the best of both worlds. And that's what they showed. They showed that, if you go and select certain parameters in this parameter from 0 to 1, you select certain value of this parameter, you can simultaneously, and if you look at the right graph, you can simultaneously have low diameter, but still have high clustering coefficient. So, there is like, say, I take P001, the diameter will be low, the clustering coefficient will be high. You go further to the right, the clustering coefficient will drop. You go closer to the left, the clustering is high, but the diameter is large. So there might be some range of parameters where you have sort of small world, but still high transitivity or high clustering. So that's the whole point. Now, then they tried to do, of course, calculate degree distribution. Degree distribution actually, because you go from very regular to random graph, degree distribution is Poisson. It's not, it's obviously not a power law. But and this also became a famous paper, and the power of this paper is that, they first showed that, look, it is possible to have both small world and triangles. And, the way to build small world is to create those long-range connections. And it's, I think, also published in Nature. Today, this is kind of, sounds like very obvious kind of statements, but back then when people just started, studying networks, that was, in some way like revelation that it's actually possible to do, right? It was very simple sort of instruments. A paper like, I don't know, even less than 1 page long. And so this is what this looks like. We take a bunch of nodes on the regular grid, and then we do rewiring. And if, for example, on the original grid with triangles, average path length was 358 and clustering coefficient 0.49, then after 20% rewiring, you can drop path length and still preserve clustering coefficient, not going to 0, right? This is just a very, simple simulation. So, bottom line, we talked about 3 different models: random graph, Barabashi-Albert model, Watts-Strogan's model. We looked at properties: distribution, power law, the degree distribution, clustering coefficient, average path length, and here they are, right? Neither of them satisfy what happens in empirical or real-world networks, right? The power law is Barabashi-Albert model only that satisfies. Large clustering is, you can have any clustering you want in Watts-Strogan's model. And small world, well, small world is a random graph. I mean, all of them can do sort of smallish world. Out of all those 3, probably Barabashi-Albert is the closest to a real-world network, but still, does not, for example, fit the bill for clustering coefficient. So the bottom line is these are models, right? So they're simplified version of reality. They're good to generate. They're generative models, which means they allow you to generate networks. You can generate to compare to real networks. You can, see if this model explains the networks, and if not, well, that means the world is much more complex than these models. But also, these models are kind of starting point for you to investigate and try to build out of those, building blocks other models. And I think these are like sort of 2 classical papers. Again, on the website we have more papers, but this is the Barabashi-Albert emerging of scaling, and it's published in Science, and Watts and Strogan's this the paper we just looked at, this connection things, published in Nature, 1999. All right, so and that's it today.